Hello, everyone. Welcome to the TG91 ICRP workshop on radiation risk inference at low dose and low dose rate exposure for radiological protection purposes. We are very pleased to see you all wherever you are and that you joined our workshop. That's great. Thank you very much. Um, I would like to give you a brief introduction in the background of the work of Task Group 91 of ICRP and give you a short brief history. And then I'll pass over to my colleagues, members of TG91, to present different chapters of the draft report, which is online on the website. But first of all, let me give you a very first introduction. And for this, I will share my slides. Okay, so this is a very timely workshop, actually. As you know, currently ICRP has a big project, and the project is to review and revise the system of radiological protection, which is set down and defined in ICRP publication 103. That's the basis of radiological protection all over the world. And we try to review and, if necessary, revise and update, modernize those recommendations. And for this, we had to identify basic questions, most important topics which we have to review to make our system fit for purpose. And this is, I think you all saw this picture quite often already. This is our roadmap. We have already identified those topics. This is the orange part here. And we are now in the process to develop those most important topics we have identified, building blocks, as we call them. And I give you one example. Now, the detriment, radiation-induced detriment, is one of the most important instruments or tools we have developed, ICRP has developed over the past decades. And we have a number of task groups working on topics which are relevant for calculating detriment. And all of those issues have to be updated. And of course, one topic was addressed or is being addressed by Task Group 91 on low dose and low dose rate effects. Why is this important for detriment? Now, if you read ICRP publication 152, which is on radiation detriment calculation methodology, you will find a kind of sensitivity analysis our colleagues from the former Task Group 102 had performed. So they investigated the various parameters and how they influence the calculation of detriment. And they also looked at DDREF, the dose and dose rate effectiveness factor. Currently, we are using a value of 2 in the system. And they checked, for example, what happens if they would set the DDREF to 1. And if you then look at radiation detriment for the various tumor sites, for the various organs, then you will see, except for one exception, that this change of factor of 2 from 2 to 1 directly translates into an increase in the detriment for the various organs by a factor of 2. The one exception is bone marrow, because for leukemia, as you might know, ICRP does not recommend to apply this DDREF factor. But for all the others, for solid tumors, we see that a change of a factor of 2 in DDREF directly translates into a change of a factor of 2 in the detriment for the various organs. And this is the reason why this building block, the value chosen for DDREF, is a very important part in reviewing and revising the detriment in our system. Now, this is the task group. Task Group 91, which was, I think, had a kickoff meeting in 2014 or 15. So this task group worked for quite a while now. And we have a lot of contributors, Tamara Asisova from the Russian Federation, Simon Bouffler from UK, Michiaki from Japan, Mark Little from the US. Kotaro Ozasa again from Japan as Kazuo Sakai, Roy Shore from the US, Quan Fusun, China, Linda Walsh, Switzerland, Gayle Woloschak from the US. And we have our technical secretary from New Zealand, Franklin. Easy. So I already mentioned the current system uses risk estimates from the atomic bomb survivors who were exposed to a high dose rate exposure and to pretty high doses, at least some of them. And to apply the risk estimates from this cohort to the setting, which is typical for radiation protection, ICRP suggested to use a dose and dose rate effectiveness factor and decrease the risk estimate deduced from the A-bomb survivors by a factor of 2, because it was felt that low dose rates are less contributing to radiation risk than high dose rates for the same dose. And this is what is TG91 all about. So the task group reviewed the scientific evidence for the low dose effectiveness factor and the dose rate effectiveness factor. Both combined were then combined into the DDREF by ICRP. We do not discuss directly DDREF, by the way. You will see that later. So we look at the low dose effectiveness factor and the dose rate effectiveness factor. And low dose, we follow a definition from Ansgar, is a dose of less than 100 milligray here, and a low dose rate is a dose rate of less than 0.1 milligray per minute averaged over 1 hour. Now, today we are here. Why are we here? We have a workshop on work of TG91, and the reason why we are here is the task group has finished a draft report of its work. And this draft report is on the website of ICRP since March 12 this year for public consultation. The report describes, as I already mentioned, the scientific evidence relevant to the assessment of solid cancer radiation risk at low dose and low dose rate. So the scientific evidence, this is important. It will be available on the website for comments until June 13. And it's now a usual habit of ICRP, different task groups, that we try to explain. Once a draft report is online, we try to explain how the report was developed and what the task groups thought is important for you to know. This is part of how we try to be open, transparent, and explain always what we are doing. All right, so we will explain the important points now. And then after that, there will be roughly 1 hour moderated Q&A session where you have the opportunity to raise questions. This is how the content list of the draft report looks like. So you will see, I will give a brief introduction on, and also on the historical development, very brief. Then we discuss cellular radiobiological studies, then animal studies, then the evidence from epidemiological studies in terms of dose rate, and then the evidence from epidemiological studies in terms of shape of dose response. And then we briefly discuss biologically motivated mechanistic models. And in the end, we will present you the major conclusions the task group developed. This is the link, just if you want to download the report and have not yet done so. And the program today reflects the content list. So we have Simon talking on the evidence from radiobiological studies, from cellular studies, Gayle Woloschak, then evidence from experimental animals, then Roy Shore and Linda Walsh on the evidence on dose rate effects among epidemiologic data, and then Mark Little and Kotaro Ozasa on the shape of the dose response in the A-bomb survivor data. And then Michiaki Kai will give you some insight on mechanistic modeling, followed by a conclusion with the major points. A very brief history. As you maybe know, NCRP in 1980 has introduced what they call the dose rate effectiveness factor, DREF, and proposed values between 2 and 10. And then Ansgar noted that such a factor varies very widely, so there are huge uncertainties, of course. And they followed this recommendation by NCRP, value between 2 and 10. And then ICRP 60, 1991, they proposed a dose and dose rate effectiveness factor with a value of 2. But acknowledging that this value of 2 is somewhat arbitrary, but it was felt that it was conservative. Ansgar followed this initially, but then later in 2006, they changed the approach somewhat and didn't apply a DDREF, but instead they used the linear quadratic dose response model, which implicitly allows for an LDEF because it allows for curvature. And then they said, okay, this approach is somewhat consistent with a value of 2 of the DDREF. Bayer 7 proposed a value of 1.5 in 2006. WHO, they did not use a DDREF at all. In Germany, the German Radiation Protection Commission suggested a value of 1 for DDREF. The CNES report in 2017, which was, I think, meant to be used by NIOSH, suggested a value of 1.3. So there are different there was a development along the line a long time, and we did a review, and this review was published in this paper here. And with this, by highlighting that we have continuously published what we felt was important to publish to inform the community, the radiation protection community, all the time what we are doing. So if you continuously read our papers, then what now is written or summarized in the report shouldn't come as a surprise to you. So with this, I would like to hand over, and the next will be Simon, introducing our work on cellular biology, cellular experiments. Simon, the floor is yours.
Thank you very much, Werner. And just let me share my screen, show slides 1 second. Oh, here we go. So the slide showing, I think.
Yes.
Yeah, great. Thank you. And good afternoon, and well, good whatever part of the day it is to all online. It's a pleasure to be able to be with you today to give you a very brief outline of the chapter really that deals with cellular radiobiological studies. So as I say, my name is Simon Bouffler. I'm currently ICRP's Vice Chair, and I work for the UK Health Security Agency in Great Britain. So, oops, let me just find. Just give me a second. I hope you found my buttons to move slides on. So, as background, the chapter covers some of the previous evaluations of cellular studies that have been undertaken, notably those from UNSCEAR, from EPRI, the Electrical Power Research Institute in the US, and the CNES report that Werner referred to just a few moments ago as well. And they were used really to draw, or they're drawn upon to identify the relevant cellular and molecular endpoints for consideration within this ICRP work. And perhaps prime amongst them was the 2020 to 2021 Annex C of UNSCEAR, which considered biological mechanisms relevant for low dose and low dose rate radiation cancer risk inference. It's really the topic we're talking about here today. Oops, just need to go back. And those collectively indicated the most secure data, which to consider in terms of relevance to low dose and low dose rate risk inference. Like DNA damage is repair, induction of gene mutations and chromosomal aberrations. And that conclusion was really broadly similar to an article published in the course of this work from Tony Brooks and colleagues, given the reference down at the bottom there in grey. Moving on, just to summarize what those endpoints were. So as mentioned briefly, DNA damage induction and repair assayed both in vitro and primarily in vitro, but some in vivo studies available as well. Induction of gene mutations, induction of chromosomal aberrations, and also cell cycle checkpoints and apoptotic endpoints were considered as well. As well as those sort of primary endpoints considered, we also looked at modulators of those phenomena and risk itself. So the non-targeted effects of transmissible genomic instability, bystander effects and adaptive responses, studies considering differential gene and protein expression at different doses or different dose rates, modulation of the immune system, relatively small amounts of work available, but potentially interesting for the future, at least, on tumor invasion and metastasis, plus tumor vascularization. So the main conclusions that are drawn from looking at the publications that have been cited, and those that have read the report, the draft report, will have seen there's fairly extensive literature cited in all sections, including this. The chromosome aberration studies overall indicate LDEF and DREF values in the range of 3 to 5. So quite wide, but within those ranges that Werner highlighted from the historical studies that have been done. There's little evidence for dose thresholds from chromosome aberration data, and few of the data available pose a significant challenge to the central role for DNA damage and mutation in radiation carcinogenesis. But there's a number of potential risk modulating processes that might serve to increase or decrease risk that were identified. The role of these processes in radiation carcinogenesis in vivo is presently insufficiently defined to bring them into considerations of health risk assessment. And then evidence from potential risk modulators that I showed on the previous slide is not really sufficient yet to allow firm conclusions to be drawn on their impact of the evaluation of dose rate and low dose effectiveness. Then the sort of further conclusions. Generally, cellular and molecular data tend to support the application of a DDREF value to estimate risk at low doses and low dose rates. So that's a positive finding, if you like. The magnitude of the dose rate effectiveness and low dose effectiveness factors is not large. Chromosomal studies, which could include some of the largest data sets that are available, indicating on average around about 4. The sound data indicating that DNA damage responses and mutational processes operate at low doses down to 20 milligray and at dose rates down to 20 milligrays per day and 1 milligray per day. As they, so those processes are operating at those lower doses and low dose rates as they do at higher doses and dose rates. And there's many processes that are likely to modulate DNA damage responses, and those, while they're currently somewhat poorly defined, could have a significant influence on the magnitude of dose rate effectiveness and low dose effectiveness. But those, as I said, are not really sufficiently defined at the moment to be able to draw firm conclusions on what the effect might actually be. So that is really a very brief summary of what was examined and what was found in the cellular biology section. And I now will hand over to Gayle Woloschak, who will be describing some of the work done in animal studies. So Gayle, over to you.
Yeah, thanks, Simon. Let me bring up my slides here. Okay. So great. So my job is to talk about some of the work that's been done with the animal studies for TG91. And you can imagine the importance of animal studies in a way because you can do this work under controlled conditions. Nevertheless, probably human is most informative, but animal work can also be critical. So there was a lot. We looked at a lot of things with DDREF, DREF, and LDEF. There are some challenges that exist in the system. First of all, it wasn't possible to really look at high LAT radiation because there's just not much of a dose rate effect. There may be at some unusual dose rates, but not at the ones that we looked at in most of these studies. Oftentimes it's very hard to get a large number of animals available to be able to do the kind of work that you need to do at low doses. So we looked a lot at large scale studies that pooled animals from different different work that had been done. And let me just say that I really encourage people to archive data, to put those data out there, because this is what's going to allow for larger numbers of animals to be analyzed for low dose and low dose rates. There was a lot of interest that's been renewed, and certainly there are accessible data sets that have been available. Now, we did look at some of the data that were not perhaps directly related to they did not do just DREF, DDREF, or LDEF calculations. We also looked at the low dose and low dose rate data that were available in the literature. Some were using transgenic animals for that work. We included some of that. I'll show you a table in a few moments. And then there are other studies that have been done that looked at low doses of animals, many times not looking at cancer endpoints, but at, for example, in this particular study, looking at atherosclerosis endpoints and other endpoints. We focused either on life shortening or on cancer. Cancer would be the most important, but we did do some life shortening comparisons as well. Now, there were some things that we focused on that allowed for improved DDREF and LDEF and DREF conclusions that were probably not done before this work, or were not done that well. First of all, there have been meta-analyses that allowed for comparing of dosimetry and animal and strain characteristics that were not possible in the past. We know that there are animal strain characteristics, particularly mouse strain characteristics, that are different for cancer incidence, for many other features. And by looking at large scale studies, we can attempt to take all those into consideration. There must be support information and supplemental information to allow us to gain the most information. And then most of the work here has been with comparisons with mouse and rat differences. There are very few broad differences between mouse and rat for the kinds of work that we looked at here. Dog studies, it seems to me, would probably be something that could be looked at for the future with some of the large scale dog studies. In addition, the data archiving is important, and archiving existing data would be really important. And I'll point that out in a moment. So the studies that were done here involved mostly comparisons of the European Radiation Archive, where they still have archived very large numbers of mice, dogs, monkeys, other species. And then our own Northwestern University Radiobiology Archive, which looks at both external beam animals and internal exposures. We used mostly external beam for these studies, although the internal exposures might be useful downstream when you consider the options that are done. So these two data sets were used for the larger scale studies. There are other data sets that are coming up, and I believe that in the future we might get even better LDEF and DEF data and DREF data if these data sets are also available and are used. There is the NASA data set that has become available. Canadian National Laboratory has been focusing on putting their animals on a website, and they have pretty large scale studies that have been done. There are efforts in Japan that, as they become more and more available, they will also be important. And I'll show you some of the data that have come from some of the studies from Japan. And then, of course, there are the Russian studies that were done in the South Urals Biophysics Institute. Those data are not really available. They're not digitized, but those animals would be very important if they could be added to the group. So let me now talk about some of the tables that were generated from animals exposed to low dose and low dose rate. And as I said, we did consider those things that were related to DREF, LDEF, and DDREF, but these were studies where they did not look at the actual DDREF or DREF or LDEF values for any of those. So these could perhaps with future analysis, or if these studies could be combined with others, could lead to significant studies. There are quite a few of these out there. This is one set, and I want to especially note the Japanese who've done a large number of studies at the up in Aomori in Japan, where they have actually a large number of animals, and have done some studies, and I will quote at least one or two of those. There are also additional studies that were done looking at low dose and low dose rate effects. So we looked at these data to make sure that they were consistent with what we were seeing from the actual studies where they calculated the LDEF or DREF. Here and you can see that there are quite a few studies. The last one was done through my own group, and we'll talk in a little bit more detail about that in a moment. So the actual studies that we could find in the literature that looked at DREF and LDEF, and in at least some examples, DDREF, and actually calculated numbers are shown here. I want to first look at the Beer-7 report, which used mice for their determination of the DDREF. They had values of 0.1 to 3.2. Those studies, you can't go back and actually recalculate. You only can see the data that are in the literature from that study. These came mostly from Oak Ridge experiments that had been done. Then there were a number of studies. The Japanese did a study where they looked at DREF. They came up with values that are around 3 to 5.7. They were looking at chronically exposed animals, and these studies are very well done. Using our large-scale data set, there have been several studies. Tran and Little came up with a DREF of 1.19 and an LDEF of 1.0. David Hull looked at DDREF in some of our animal systems and some of the others in the literature, came up with values of 2.3 and 2.4. My own Ben Haley from my own group, he looked at a Beer-7 recalculation based on larger numbers of animals, came up with DDREFs that are anywhere from 1 up to infinity. But then he did a smaller study that focused only on direct comparisons of acutely exposed to protracted exposures in animals, and came up with a DREF at around 2. So you can see the ranges of the animals are very similar to the kinds of ranges we've been talking about in most of these examples, and therefore give us a good range. I would say that between 1 and 2 was the majority of where the studies fell. So when we think about things to think about for the future, combining studies of animals for large data sets is going to be very critically important for this work. Very rarely can a single experiment do enough work to give enough low dose rate and low dose experiments or animals to be statistically significant. So combining studies is critical, and it was for these studies as well. The variations in low dose and low dose rate in cancer incidence may vary with different rodent systems, because different strains of animals have a tendency to get certain kinds of cancers. That obviously needs to be considered. And there are many factors that influence low dose exposures, including genetic background, diet, and I won't go into it, but we've compared some data that show that diet makes a difference in these animals. Overall health is important. The animals are needed. Doses may be significantly different from one species to another, which is from one strain to another and from one species to another. So doing strain-specific differences, there are different LD50s for different mouse strains. But then if you're comparing mice with eventually perhaps dogs or even monkeys, the dose effects are very different. Transgenic models should be added into this, and a large-scale data study that includes the NASA work, the Japanese chronic exposed animals, perhaps the Russian study. I believe those would be very important for the future. And with that, I'll end, and I'm going to turn it over to Linda and Roy, who will talk next. Let me stop my sharing and take it away, Linda and Roy.
Okay, well, I'm going to talk about dose rate effectiveness factor and how we looked at epidemiologic studies to try to estimate that. Okay, next slide. Well, the basic procedure we used to try to estimate the dose rate effectiveness factor, or DREF, was to compile all the low dose and low dose rate studies that we could find in the literature. These were studies of radiation workers or of environmental radiation exposures. We then compared each of those, what I'll call LDR studies, with the corresponding risk estimates from the Japanese atomic bomb lifespan study. And in doing that, we calculate the ratio of the low dose rate study to the LSS study. But when we get done, we'll estimate the DREF by inverting that and looking at the inverse of that, of the ratio that we come up with. Okay, next slide. Well, how did we select studies? We wanted to avoid the issue of sort of cherry picking studies that fit our preconceived notions. So we included all the LDR studies that we could find in the literature that had dose response analyses for all solid cancer. And we found 24 LDR studies of solid cancer mortality and an additional 5 studies that reported only solid cancer incidence results and without any mortality analysis. So that gave us a total of 29 LDR studies. Next slide. Well, how do we do it? This is more methodology. For each LDR study, we calculate an adjusted regression estimate of the radiation risk in the LSS study. And the reason for that is we need to adjust for the mean dose that the LDR study had, the percentage of females, which typically differed from the lifespan study, the LSS ratio, because there are more females than males in the LSS in general, but not in worker studies. And also adjusting for average age at first exposure and average age at latest follow-up. And so for each LDR study, we could calculate its risk estimate and then the adjusted LSS study risk estimate that went with that. And so then we could form a ratio for that study of the LDR to the LSS and calculate an appropriate confidence interval on that ratio. Next slide. Then to conduct the meta-analysis, we used the conventional meta-analysis method, but the meta-analysis weights according to the inverse of the relative precision of each of those LDR to LSS ratios. The issue we confronted was that the MIAC worker study had a large weight in the meta-analysis. But we didn't want a meta-analysis that was mainly just a MIAC worker study. We looked more carefully at that study, and we saw that at two particular facilities at MIAC, the radiochemical facility and the plutonium production facility. They had very high cumulative external doses, averaged over 400 milligray cumulatively, and they often had high plutonium exposure as well. So we decided we needed to conduct the meta-analyses several different ways. One including all the MIAC workers and of course all the other studies. And the second way was to include all the studies, including MIAC, but to exclude the radiochemical or plutonium production facility workers. And then finally, we looked at only the studies that had mean cumulative doses under 100 milligray, which fits the definition of low dose studies. And in doing that, that excluded the MIAC worker study and the Russian Chernobyl cleanup worker study. So there were two fewer studies for that. Okay, next slide. Well, the results we got for the dose rate effectiveness factor then for all solid cancer from these meta-analyses are shown here. When we included all MIAC workers and looked at only mortality, the ratio, the DREF ratio was 2.0, excuse me, and very similar when we looked at mortality and incidence studies of 1.9. When we excluded the radiochemical and plutonium production facility workers, then the ratios changed some, 1.4 for mortality studies and 1.5 when we included the incidence studies as well. And finally, when we looked at studies with only the ones that had mean cumulative doses under 100 milligray, we came up with 0.9 for mortality and 1.3 for mortality plus incidence. Now, one thing you'll notice in this table is that only one of the analyses has an upper confidence bound that's greater than 3, and that was the mortality studies with all MIAC workers. All the rest had bounds that were 3 or less. So next slide. So our tentative conclusions are that the results are not compatible with a high value of a dose rate effectiveness factor, such as greater than 3, because as I just said, almost all the estimates excluded values greater than 3. Perhaps the most important thing, though, is that we can't differentiate a dose rate effectiveness factor of 1 versus 2. You could see with the different epidemiological subsets that some were close to 1, some were close to 2, and some were in between. And that occurred because there was a fair amount of heterogeneity in the ratios for the different LDR studies. In addition, there are other sources of uncertainty in this analysis. For instance, we're comparing risk estimates across populations. We're comparing the Japanese LSS study and their rates for total solid cancer with Western world nuclear workers. And there are differences in the distribution of types of cancer between the Japanese population and the Western world's populations. Secondly, there are dosimetric differences. For the atomic bomb, there were the doses were several MeV, whereas for workers, they're typically only several hundred keV. And it appears that there may be some differences in the effectiveness of radiations that vary between in that range. So we concluded that we couldn't draw any conclusions other than simply saying we can't tell the difference between a DREF of 1 and 2, but we can say that we see little evidence for very high DREF values. And I think that concludes my presentation. The next slide. So thank you very much. And next will be is Mark Little here, or are you going, or is Werner going to take it? I'm not sure.
I am here. Right. So what I'll be talking about is the work that I did with Kotaro Ozasa, ex-RERF and now at Kyoto Prefecture University, looking at the evidence of dose effects, not dose rate effects, looking at dose curvature analysis. Could we have the next slide, please? So the analyses will be focused on one particular and very important data set, the Japanese atomic bomb survivor mortality and incidence, solid cancer mortality and incidence data. Today I'll briefly introduce the methods of analysis that we use for these data sets and give you some thumbnail results and conclusions, and that essentially is the introduction. Could I have the next slide, please, Charlotte? So this slide shows the dose response in the current the lifespan study 14 mortality data in the from the A-bomb survivors. There is, as you can see, a highly significant dose response with no indication really of any threshold. You can exclude thresholds of more than about 0.15 gray. And there are weak indications of upward curvature, particularly over the lower dose range, 0 to 2 gray. Could I have the next slide, please? So I'll describe a number of different methods of analyses. The first, we try to get some handle on the dose and dose rate effectiveness factor by assessing the curvature in dose response, and we did this by the so-called low dose extrapolation factor, which is just defined as what you get by fitting a linear model to the data, and then considering the linear coefficient from fitting a linear quadratic model. So it's that the ratio between between these two gives a measure of the upward curvature. A linear model fitted to over the whole dose range will tend to be higher than the linear coefficient from fitting a linear quadratic model. So could I have the next slide, please? This gives a bit more detail about the particular types of model used, both for the mortality data, the current mortality data of Ozasa et al., and also the various sets of instance data, the corresponding to the current as it was cycled of instance data publications, the papers of Grant et al. In 2017 and 2021, and the Cahoon et al. Lung cancer data 2017. So as previously, we do this by fitting linear and linear quadratic models, adjusting for the effects of age, age and exposure, and sex, with a semi-parametric adjustment for the background, as shown by the formula at the bottom. So that's the one method of analysis. Can we have the next slide, please? The other method of analysis uses sort of a method that I developed for the UNSCEAR 2006 report in fitting to the then current lifespan study mortality data, the recently released data using DSO2. So it's using a Bayesian Markov chain Monte Carlo approach, taking account of the classical dose errors in the lifespan study. So the idea is that we fit this a model now over the linear quadratic model, both a relative risk and an absolute risk model, to various types of solid cancers, both solid cancers and various subtypes thereof, and we assess the predicted population risk from this linear quadratic model at various test doses. So we assume we look in particular at the dose of 1 gray and then the low dose, the 0.01 gray. And so looking at how the predicted risk varies over that for those two test doses and an intermediate dose as well, gives you some idea of how the cancer risk will vary with dose. So could I have the next slide, please? So this slide shows the results of fitting a linear quadratic model to the Ozasa et al. Mortality data, looking in particular at at what happens if you fit it over the full dose range, that's 0 to 4 gray, and over the lower dose range, 0 to 2 gray. The thing to look at here is the middle column, the ratio of the quadratic to linear coefficients in each of the blocks of results. And as you can see, in going from the full dose range to a reduced dose range, you get in general this ratio of quadratic to linear coefficients increases, and there's slightly stronger indications of curvature. As you can see, there is significant curvature for all solid cancers over the 0 to 2 gray range. Indications of curvature only really for colon cancer for the full dose range. Okay, next slide, please. So this now this slide we fitted the this is work, by the way, that I did with Nobi Hamada, published in a paper a few years back. We looked at fitting the linear and linear quadratic models to the current mortality data over a slightly lower dose range, 0 to 3 gray, and so and as I stated a few slides back, we calculated the low dose extrapolation factor, the LDEF, as the ratio of the linear coefficients from the full dose range model fit. In other words, as shown in the leftmost column, to the linear coefficient from the linear fitting the linear quadratic model, and so the ratio of those two is shown at the right. And as you can see, that there are in general fairly modest LDEFs ranging from about 1 to a bit over 2. the LDFs are largest for the this remainder category of all solid cancers, excluding lung, stomach, and breast. Right, could we have the next slide, please? Oh, hang on. Yes, that's right. Yes, so this now shows the results of fitting the same sort of model now, but now to the instance data, again over the 0 to 3 gray range, so not quite the full dose range. And again, what I show is the results of fitting the linear model right at the left, and then the linear quadratic model in the middle of the table, and the ratio of the linear coefficients from the linear to the linear quadratic model at the right. The picture is pretty similar. I'd say generally modest LDFs of up to about 1.3 for various solid cancers sets. Now we turn. Could we have the next slide, please? Now we see the results of fitting the Bayesian MCMC models to the current lifespan study 14 data. This is a analysis somewhat analogous to that done for the UNSCEAR 2006 report. So what's shown here are the population risks for various test doses, as shown in the column towards the left of the table, so 0.01, 0.1, and 1 gray, for various solid cancer groups, and then this done using both generalized relative risk models and generalized absolute risk models, shown the middle and the right respectively. So what you can see is that in aggregate the risks reduced by about a factor of 2, going from a test dose of 1 gray to 0.01 gray, whether using absolute or relative risk models. Some cancer sites, for example, the remainder category of all solid cancers, excluding lung, stomach, and breast, as shown at the bottom, show a larger reduction than this, but some, for example, breast and stomach, show somewhat less reduction in risk, going from the 0.1 to 1 gray to 0.01 gray test dose. So I should just emphasize that this is not the same thing as LDF, but it does nevertheless give an indication of curvature in the dose response in this data set. So could we have the next slide, please? Right, so just to conclude, we've seen that there's stronger indications of curvature over a slightly lower dose range, so 0 to 2 gray or 0 to 3 gray, and some indications of curvature in the mortality data, but with fairly modest LDEFs, generally under 2.5 overall. Generally pretty weak indications of curvature in the instance data, as indicated by LDFs, sort of generally in the range 1.2 to 1.3. And finally, the reductions in population risk from models fitted to the Bayesian models fitted to lifespan study 14 data by about a factor of 2 overall, in going from a test dose of 1 gray to 0.01 gray. And I think that's my final slide. So perhaps if at that point we could pass on to, I think it's Michiaki K.
Thank you. Okay, can you my slide? Can you see my slide? Okay.
Looks great.
Okay, I'm a Michiaki from Japan. I'm now a main commission member. I work at Nippon University. Today, I would like to talk about the studies on biologically motivated mechanistic models. Biological-based mechanistic model for culture genesis have been used since 1950s. The model were used to discuss the process of culture genesis in a quantitative way. Specifically, age-specific motility was discussed. In 1990s, Nording proposed a 6 or 7 mutational cellular change to develop a cancer. Currently, it is well known. Armitage and Dorr develop a mathematical formalism. Multi-stage theory culture genesis incorporated selective advantage of mutational cells, and the two-stage coronal expansion model was proposed. The two-stage model was used to explain the occurrence of retinoblastoma. Murgafka colleagues conducted mathematical development and application of the two-stage model. A multi-stage theory of culture genesis model assumes several mutational steps are needed into cancer cells. After latent period, cancer cells develop into clinically detectable cancers. Mathematical formula of age-specific incidence is expressed as a power function of age. This figure of age-specific incidence is expressed. The figure shows a log-log plot of colon cancer incidence. Age trend is roughly linear. The slope of line is determined by the number of multi-stage mutational steps. In this model, there is no consideration of cell dynamics. So, two-stage model was developed. Two-stage coronal expansion model assumes intermediate cells mutated from normal cells undergo cell division, cell death, and cell differentiation. The concept of initiation and promotion in culture genesis can be included in the model. Arbitrary type model need 2 parameters. On the other hand, two-stage model require 4 parameters. When you consider stochastic process, mathematical formula of age-specific incidence is expressed by 2 exponential terms as a function of 3 parameters related to cell dynamics. When you consider radiation culture genesis, you need to think about which processes are affected by radiation dose. Next, I will talk about several studies on radiation dose response using biological motivated mechanistic models. In particular, the model will apply to human epidemiological data. Atomic bomb survivor data in Hiroshima and Nagasaki are main cohort to discuss the model performance. The first application of the two-stage model assumed radiation acts linearly with dose on initiation. This initiation hypothesis indicate a good fit to data. However, RERF data, Ebon survivor data suggest a number of models, including a multi-stage model, can describe cancer incidence equally well. Interestingly, the model analysis suggested higher evidence of radiation action on promotion than on initiation. However, mechanism promotion effect was unknown. The related model analysis assumes cell inactivation in addition to initiation. This study showed most of preferred model can describe the data better than preferred empirical risk model. The more sophisticated model first study focused on the cancer risk pattern as a function of age at exposure in Japanese atomic bomb survival. New formalism was developed by assuming radiation initiation, promoter, kill pre-malignant cell generator clone. This study suggests promotional process become increasingly important as age at exposure increases. Next study consider genomic instability. This model considers two pathways. Cells with genomic instability in addition to initiated cell pathway. Main effect of radiation-induced genomic instability is to increase the rate of transition of non-initiated cell to initiated cell with a proliferative advantage. A similar concept of the model with genomic instability was proposed by Kaiser's group. It assumed there are two molecular pathways, microsatellite instability, chromosome instability. This study focused on the colon cancer. It used an extended two-stage model, which incorporated two molecular pathways, microsatellite instability and chromosome instability. It assumed coronal growth of adenoma occur in intermediate cells. This study showed that chromosome instability pathway exhibits a strong radiosensitivity. Among young birth cohort, the excess absolute risk-related chromosome instability is larger by an order of magnitude compared to the microsatellite instability-related risk. Other model analysis. It is interesting to see the long-term exposure model analysis. Fractionation of dose increases cancer excess relative risk because repopulation, both normal and pre-malignant cell, during interfractional interval compensate for much of cell killing. This result might suggest fractionation should be differently treated with chronic exposure. Model analysis of Tetra cohort, Chernobyl cohort show that it is now possible to incorporate molecular biomarker in this assessment. On conclusion, biological motivated model will be useful tool to quantitatively discuss radiation risk. In almost cases, numerical value are biologically plausible. And in many cases, they perform similarly better than descriptive model. And it's good description investigate endpoint as a function of time since exposure. The assumed mechanism might play some role in cultural genesis. Two-stage clonal expansion model can provide robust risk estimate without additional assumption and offer inherent flexibility to add more stage, 3 or a 4-stage model. Various option radiation action, including a non-linear process, can be tested in human cohort in the future. We expect the approach of using this biological-based model will continuously benefit in the future from growing knowledge on calciogenesis. This is the final slide. Current knowledge of calciogenesis and its mechanism is too limited to explain the process of calciogenesis as a quantitative mechanism. Even if the radiation action is assumed linear, the overall dose response is not necessarily linear. If radiation acts different process of calciogenesis, the dose rate effect, considering fractionation, is needed to be further investigated. A systematic investigation of implication of mechanistic model on dose response is needed and currently being performed by the authors. Thank you very much. I pass it over to Werner. Next will be Werner.
Yes. Thank you very much. So now we come to the major conclusions. But before I'm doing so, please let me first emphasize that this task group, they did a thorough review of the literature in many ways, and you heard about that. But this task group did much more. So they did also own analyses. We heard that this task group did for the very first time pooled analyses of historic animal data, because the databases in the US and in Europe became available when the task group started. This group did own analyses of epidemiologic studies in terms of a meta-analysis to compare the high-dose rate study of atomic bomb survivors with low-dose rate, for example, nuclear worker studies and others. And the task group also did own analysis of curvature using most recent follow-up data from the atomic bomb survivors. So this was a huge effort, and we published along the lines. Every time when we felt we got a result worth publishing, we did that to inform you, to inform the community. Now, you already saw in the presentations that none of the colleagues presented a magic number from their analyses. And this has to do with a second important aspect, I believe, because ICRP wants to be transparent also in terms of the uncertainties behind the work done by ICRP. And this is now an example. So we heard ranges, we didn't hear any magic numbers so far. And in this spirit, I will continue now and I will present you the final conclusions developed by the task group. And this was reviewed already extensively reviewed by Committee 1 of ICRP on radiation effects, and also by the main commission. Otherwise, it wouldn't be put on the website for public consultation. So what are the main conclusions? Let's go through them in detail. First point, this report evaluates the current scientific evidence. So we focused on science here, on low dose and low dose rate biological effects of ionizing radiation in terms of the low dose effectiveness factor, the LDEF, and the dose rate effectiveness factor, DREF. So we looked at low dose effects and low dose rate effects separately. We looked at various endpoints related to the risk of all solid cancer at subcellular, cellular, tissue, and organism and population levels. And I already mentioned what we consider as a low dose and a low dose rate. What we did not do is the concept of DDREF, which is the combination of LDEF and DREF, invented by ICRP, developed by ICRP, which is basically an approach to be applied for radiological protection purposes, is not the focus of this report. This is important for you to keep in mind once we come to the discussion section. In particular, the rationale behind this approach and its implication for the system of radiological protection is not discussed here. So we focus on science. Now, for somatic cell mutation, cell transformation, and cytogenetic endpoints, numerical evaluations of both DREF and LDEF provide values around 4 and below. This was pretty much consistent, but there is no one number. You heard about the ranges of values we found. Now, in terms of the pooled analysis of data from experimental animals, the analysis mostly suggests an LDEF close to 1 and a dose rate effectiveness factor between 1 and 2 for life shortening and for all solid cancers combined, but with considerable variation depending on tumor type. Next main point. The recent meta-analysis of epidemiological data performed by the group for all solid cancers point toward DREF values between about 1 and 3, taking account of the uncertainties involved in these estimates. And you heard about those uncertainties as well. We would like to be transparent. Analysis on curvature in the incidence and mortality data from the Japanese atomic bomb survivors and most recent follow-up data find consistent evidence of curvature so that evaluated population risks per gray for all solid cancer mortality evaluated at 1 gray are about twice as large as those evaluated at 10 milligray. This is not exactly an LDF as we heard, but it gives you an idea, an indication. They tend to support a sex-averaged LDEF value of between 1 and 2 for all solid cancers combined. But again, if you compare different cancer sites, different tumor locations, then there is quite some variation. And now maybe the main point of the main points, of the major points, the last most important final conclusion in the report is, and I read that because wording is also important here, while considerable uncertainties remain, the ranges of LDEF and DREF values obtained here are narrower than those obtained in previous evaluations. This has to do, of course, with improved scientific evidence. The overall conclusion of this report is that, based on current scientific evidence, again, scientific evidence is the key here, LDEF and DREF values much larger than 3 or less than 1 are unlikely. So if we take all the results together from all the endpoints we looked at, all the endpoints, they have advantages and disadvantages, but we thought we should look at the overall picture. And this was a process which was open. So we really did everything we could to collect data from various sources in an open way. And so we didn't do, as Roy mentioned, cherry picking. So we tried to include all the available information. So based on current scientific evidence, LDEF and DREF values much larger than 3 or less than 1 are unlikely. These ranges appear largely consistent for the various sources of data reviewed in this report. And in a way, this is good news, because something with between 1 or 3 is consistent with the scientific evidence means that the value of DDREF we are currently using in the system of 2 is not too bad. The bad news, if you like, is that, and this was also pointed out, I think, by Roy or others, we cannot really distinguish from the scientific point of view. We cannot really distinguish between a value of 1, which was often suggested, and 2, which was also suggested in the past. And this is just the reality we found. You may like it or not, but this is we have presented now our results in the most honest and transparent and open way. And now, with this, I think the floor is open for discussion, for questions and answers. And we invite you to send us, as pointed out by Kelsey, to send us your questions. And I guess, Kelsey, you will moderate and have a look at those questions. But until we enter this Q&A session, thank you very much for listening. We had quite a number of participants, more than 500 for sure, for most of the time. I don't know how many we have now, but thank you for listening so far, and I'm looking forward to the discussion.
Perfect. Yeah, I'm happy to moderate. It might be easier for you to also look at the questions, just because you might know better who's best to answer each one of the questions. So again, if you do have questions, feel free to use the Q&A function. We will do our best to get to everything in the time allotted. We still have about 37 minutes, I believe. And so if anything, if we don't get to anything today, we will do our best to respond with text on the event web page after the event, once we post the recording, which will also be available. So I'm assuming this first question was probably best suited for Gayle. How does ICRP justify using animal data to set radiation dose limits for humans? And do you believe this approach is scientifically sound?
Yeah, and there's also another question. The third question, the animal in this study has the same species or race. Let me try to take both of those at the same time.
Perfect.
So the value of using animals, and I tried to say this, but probably didn't say it very well, is that in animals, you can do carefully controlled situations. You don't have to worry about animals smoking unless you want them to, of course. You don't have to worry about whether they've had exposures to alcohol or other things. They're in a closed environment where they're not exposed to other things. So you can get a good estimate of what the effects are of just the experimental conditions. The problem, of course, with animal studies is that a mouse is not a human, a dog is not a human, a monkey is not a human. And so we must then extrapolate. One thinking of an approach to allow for better extrapolation is to do that comparison between what we try to do in this study. Here you have what the humans have. Is there anything in the controlled animal studies that's inconsistent with it? And the answer was generally no, it wasn't. In terms of which animals were used, the data, I presented many studies there. Most of the data were from mice. One study combined mice and rats. It didn't show a difference in the DDREF for rats. That was that one Haley study. That study was looking at life shortening. The one by Haley that was looking at cancer did not include rats. So those two. So there are other data sets that can be applied, but those are going to be more complicated because there just aren't enough for the external exposure. So I hope that answered the questions.
Thank you, Gayle. Again, just a reminder, I just see some are raising their hands. Please use the chat box or the Q&A function that's on the bottom toolbar. I'm not sure who best to answer this, but how is it applied radiation protection for radiological examination? Will it be used as a dose constraint or dose limit value?
I can make a quick stab at it. I mean, most of the work that we do for radiological examination, involves diagnostic X-rays and things like that, which are given at a very high dose rate. So therefore, the DDREF is not likely to have a big impact there.
Perfect. Thank you. Great. And just for Simon makes a great idea too. If there is If you, the panelists that are on here, if you review the Q&A, there should be an option for you to say answer live, which basically means that you would like to answer this question. So Simon has done so. So on cellular and animal, Japanese low dose rate data, especially of chromosomal aberration in chronically exposed mice, have shown increase with dose at 20 milligray a day and 1 milligray a day, but not at 0.05 milligray a day, roughly 20 milligray Kerala annual dose rate. These results should be given more consideration. Simon.
Sure. Yeah. Thanks, Kelsey. Yeah, I was in fact trying to type an answer, but I pushed the wrong bit. Anyway, very happy to answer verbally. The chromosome aberration studies are certainly taken into account in the chapter that I was talking to a little bit earlier on. But I think the point of the general point I would make is that, you know, these are one contribution to a much larger sort of pool of data we have to look across. So I think we will go back and revisit whether the studies you mentioned, Toshi, are covered adequately. But do bear in mind, it's you know, that's one set of studies amongst a much larger group, and I think that would apply to the animal studies as well as the cellular. But I don't know if Gayle wanted to comment.
Thank you.
Thanks, Simon. I think you said it very well.
Perfect. Want to organize? That maybe not the question. Okay, here. Thank you all for the interesting presentations. Based on the studies conducted by you all, is there any conclusion that can be done considering the yearly effective dose limit for exposed workers, which is below 20 millisieverts, or medical practices, which is of the same magnitude? What would be the recommendation review on the safety recommendations for safety radiation protection systems, considering the limits currently stated?
Maybe I can step in here. Of course, this is the elephant in the room. What does this mean in terms of dose limits, for example? And I mentioned in the beginning that the DDREF, the choice of the DDREF value, will directly translate into the detriment proposed by ICRP, and this will have a direct influence on, for example, the final decision on dose limit. So far, what this group did, we just focused on the scientific evidence, and we were not able to come up with a single number. This is simply the truth. In the end, most probably we need a single number in the end, once we propose the new, better or updated system. And this will be finally up to the main commission at that time. We decided in the main commission, and the current main commission, we want to see all the different parameters which go into the calculation of detriment on our table. And DDREF is just one. There are more, and they may go in different directions. And once we have all the relevant parameters and results from the various task groups on our table, then in the main commission, we have to put everything together and then come up in the very, very, very end with a recommendation, for example, on dose limit. We are not yet there. And if we had hoped to get some magic number today, you may be disappointed, but that's the current status. And the main commission will get back to you in due time once they know what to do with all the results from the different task groups. I can say you that we have already established a working party or starting thinking about how to put everything together. And this will be a major task of this working party under the main commission. I hope this clarifies the situation or the meaning of the current result for the future.
Thank you. And also from the same attendee, thank you all for the brilliant presentation. Based on your studies, is there any indication of what could be, and you may have touched on this, the future effective dose limits for exposed workers, considering the safety? Would they be the same between 1 and 20 millisieverts? Would it be higher or lower? What changes could be expected on the safety radiation protection system that deals practices of low dose radiation below 20 millisieverts? So I think you touched on that a bit, but so kind of same thing. Okay, so we can move on to the next one here. I'm a medical physicist working on in a 700-bed community hospital. Last month, a paper on projected lifetime cancer risks from current computed tomography stated that in the future, 5% of induced cancer might be due to CT scan exams. Will these results be modified by your work or not? They use RAD-RAT risks model estimation. Well, if anybody wants to speak to that.
Sorry, could you just repeat? I just read some of the comments and thought how to answer those. But
I'm a medical physicist working in a 700-bed community hospital. Last month, a paper on projected lifetime cancer risks from current computed tomography stated that in the future, 5% of induced cancer might be due to CT scan exams. Will these results be modified by your work or not? They use RAD-RAT risks model estimation.
well, I understand that this was a result of a study. And what we did will not change the result of a study. Our intention was to provide a basis for a change, if necessary, or an improvement or a modernization of the system of radiological protection. Maybe I misunderstood.
I don't know. It didn't specify the exact report so much as just the title of it, but yeah. So Gayle, you put your hand up for this one. How do we take also into account work of Calabrese and work of Bobby Scott, Ontario, Canada, on low dose and cancer induction? There seemed to be a polarization there. It's interesting as a non-expert point of view.
Yeah. So let me say, first of all, that most of the calculations of DREF, LDEF, and DDREF that were done in the reports shown here would actually take into account any beneficial effects that you might find from radiation, because we're looking only at cancer from the end of as an endpoint. So if we were to see a beneficial effect of radiation, it would be evident in these large scale animal studies. There wasn't much of it that was seen. There was a little bit, but what I would argue is that a lot of the work, particularly Bobby Scott's work, is done with internal emitters. And we actually have published beneficial effects of radiation with internal emitters in dog systems. And I have been a big advocate for the fact that internal emitters and external beam are not the same and have different biological mechanisms associated with them and require additional studies. Notice that for the work that we've done here, most of it is for external exposures and not for internal exposures. It looks like Mark wants to respond as well.
Yeah, I'd like to add, this is Roy Shore. I'd like to add that we made an attempt to look at the literature broadly to identify all the relevant studies that we could, and to proceed with that. I think there's been a tendency by Calabrese and Scott and so on to use a small subset of studies, what appear to be ones that fit their preconceptions, I would say, and we don't regard that as an appropriate way to proceed in trying to evaluate the risk overall.
So Mark raised his hand. Maybe Mark, do you want to add something?
Well, yeah, just to confirm that the extend what Gayle said about the animal studies. I mean, the human data will in general include both detrimental and beneficial effects. It's all we can say is what's observed in the data set. Just a brief point in relation to the study you referred to. I think this is just a modeling exercise looking using RAD-RAT. So there's no, in fact, it's not really an epidemiological study. It is just an assessment of what risk would be if as resulting from CT scans. So I don't think that's really telling us anything about what's actually predicted by for example, the lifespan study data or the occupational data that Roy summarized.
May I just add to this, because I also see that someone said there seemed to be a polarization there. And now chairing this task group since 10 years now, I can really say from the bottom of my heart that or that there was no polarization. It was an open process. So we looked at the literature as a whole, looked at all relevant endpoints we thought to be of relevance for carcinogenesis. We looked at all epidemiological studies we found informative, and simply at very low doses, epidemiology cannot give you the final answer. So, but we included everything we could. And when I started, my hope was that finally we can come up with a decision of whether ICRP should use 1 or should use 2. And in the course of our work, I had to give up this goal, because in the end it turns out that there are uncertainties. Man, that's science, and we decided to communicate those uncertainties as honestly as possible. And this is the result, what you heard today. But I can absolutely confirm there was no polarization in this respect.
Thank you, Werner. And I'm not sure, Simon, there was a question about communicating these results to patients and
I was just going to briefly touch on that. I mean, my basic point is that, in communication with patients in particular, the clinical staff should always be clear on both the risks and the benefits. In diagnostics, at least, risks are going to be small, but they're not zero usually. And the benefits often, always will outweigh the risks, given a correct application of the procedures. So I think it's about transparency. With the radiologists, you might want to, I don't think it's appropriate to go into the detail we're talking about today. You might want to go into a bit more detail about, the comparison of, the modification factors that are applied in coming up with the final risk estimates that Werner was talking to in one of his more complicated slides. And we are looking at all the components that go into that final calculation of the risk and the detriment.
Thank you. Just trying to... I have a question. Read the LQ model, linear quadratic relationships with a peak above which cancer induction declines at high dose rates. Until what dose would linear quadratic modeling be applicable? Since some assays, I assume that means, also show poor modeling at higher doses.
Shall I address that? Well, the evidence we saw from the Japanese atomic bomb survivors is that the linear quadratic model fitted quite well up to about 3 Gray. Above that point, there seems to be some for some sort of, cancer sites sort of tailing off in the dose response. Whether that's due to some sort of cell kill effect, or it could be the effect of errors in dose, which could be more extreme at high doses. We're not quite sure. But anyway, for whatever reason, that's why we decided to limit assessment of the dose response to the relatively low dose, still moderate dose region, 0 to 3 Gray for most analyses. Does that answer your question?
I'm not sure personally, but maybe whoever had written that can do a follow-up if that's the case. There's a few questions, I believe, on Monte Carlo based simulation. What role do Monte Carlo based simulation tools play in modern radiation therapy? Are they integrated into treatment planning for cancer patients?
Well, my first take would be, yes, of course, Monte Carlo methods are becoming more and more important. But this is not the topic today. I mean, today we didn't talk on how to calculate doses, for example, with Monte Carlo in radiotherapy settings. So today was a totally different topic.
Certainly.
But maybe someone else could help or find a better answer here.
If anybody thinks of something after the fact, we can always, again, we'll provide a report of the questions, questions asked, and if there's anything that we need to add on with text, we're happy to do so as well. Again, I'm not sure that, again, it's been discussed from a conclusion perspective, but what is the conclusion? Is there a difference on DDREF for male versus females, respectively? Is there a mechanistic support for acute versus protracted exposure?
So that's also a good question. I mean, as I said, we are not discussing DDREF in the report, but of course, this is another elephant in the room. I mean, if the radiation-induced risks are different for males and females, and we have some evidence, how in the end will this translate into the system? And for the moment, I can give you a clear answer. We don't know. We have other task groups. Simon is chairing 2 of those task groups on individual radiosensitivity, for example. And this is a topic, is one of the, as we call it, building blocks, one of the important issues which we have to address and which have to be on our table in the main commission before we can come up with final decisions on consequences for the system. I'm sorry but that's the current situation.
No, certainly.
Yeah. Shall we just expand a little bit on that?
Sure.
In the fact that it probably, I think early next year there should be a similar sort of workshop to this one on the evidence review on variation in response, which includes the question of male versus female. So you can look out for that. Hopefully it'll get approved for consultation in October of this year. On the second part of the question, is there mechanistic support for acute versus protracted? I think differences, is what the question is about. I think basically, yes, I don't think it's time to go into detail here, but one can make sort of logical arguments around differences between acute and protracted.
Thank you. And Mark, you have your hand up as well.
Yeah, sure. Just to touch on at least the male versus female differences. I'm not sure that there are very, very major differences, but I mean, the analysis of Eric Grant of the incidence data suggested that males had a slightly stronger sort of more pronounced upward curvature than females. A recent paper of mine and Nobi Hamada looked at this both for the mortality and incidence data, found pretty similar evidence of curvature for both mortality and incidence data in males and females. So I'm not sure. I think the evidence is out there. There may be sort of slight differences, but not major ones in estimates of curvature for male versus female.
Perfect, thank you. And then Gayle, the next question up, you had raised your hand to answer. It was regarding animal data on pigs from the Radiobiological Institute in Oxford from the later 20th century onwards.
Look, I would love to have my hands on those data and be able to look at them. We included only data sets either that were done as a summary in a paper that was published or data that we could go back and account for each animal that we could then add to our experimental group. If you have information on those pigs, please send them to me. I have data from pigs from PNNL that we have that are not yet out in the literature, that we haven't yet analyzed, but it would be great to be able to compare those. That would be a really wonderful study. Please email me.
Yes, and of course, maybe not everybody has the contact details of people on this call, but if you are here, you would have gotten a email from me inviting you to attend the Zoom. So you have my email address. So if you would like to contact or share something with one of the speakers today, do feel free to email me, and I will do what I can to connect you in the cases of something like with Gayle just mentioned. So. Moving on, Simon put his hand up for this question. Has much data on DNR repair rates and background variation on DNA damage pre-exposure been included in the analysis, for example, with gamma H2X studies?
Yeah, thanks. So the cellular radiobiology chapter does review some of the gamma H2AX and other foci sort of type assay studies that are out there. And does include, I think you mean by pre-exposure, sort of adaptive response type protocols. So yes, basically they are covered.
May I step in, Kelsey, because there was one question on LNT, on the linear no threshold model, and what's our position there? Now, as you may already understood, we have looked at linear quadratic models in our analyses. So we looked at that. And there is also several paragraphs or subchapter on threshold. And to put it in a nutshell, we didn't find any convincing evidence for a threshold in the epidemiologic data. I hope I formulated this right, Roy, Linda, Mark, our epidemiologists. And again, I mean, there was no bias in our views, I can tell, and there was simply no convincing evidence for that.
Perfect, thank you. Yeah, and there is a few mentions in the Q&A function here about LNT specifically, and some of the news with the executive order this week. And I mean, I'm not sure how relevant it is to the study, but we will hopefully maybe get to some of those towards the end. There is a lot of questions, and I can assure everyone that we will not get to all of them today. Thank you very much. This is a very active Q&A, and we will, like I said, provide the speakers with a detailed report afterwards so that we can hopefully answer some things over text and provide them on the event webpage in due time when they're available. I know that there was one, sorry for Michiaki for you. I just got to go back and find it here. Did I understand correctly in Dr. Kai's presentation that for a given dose fractionation might increase risk?
Thank you, Christian. Yes, you are right. But in this, be careful that in this study that the high dose area, and it is not clear that in the low dose rate and the exacerbation. Okay.
Wonderful, thank you. Okay, we did that one with Simon. I know that you are not looking at DDREF, but in many circumstances, low dose exposures will be delivered at low dose rates. If each factor is greater than 1, would you expect the combination effect to be multiplicative?
Now, if you, I can start. If you, for example, use a linear quadratic model and then calculate low dose, the LDEF, and if you do the same for low dose rates for fractionated exposures and also continuous low dose rate exposures, then you find that at very low doses and very low dose rates for LQ model, both formula get more and more similar. And I think this was one of the reasons why ICRP then finally decided to combine those two with one single factor. That would be my answer. So at very low doses, low dose rates, they get similar.
Perfect. Gayle, you had the next one here. How to transfer data result from animal to radiation workers and general public for low dose and dose rate effectiveness?
Yeah, I think it's a really good question, and it's a very difficult question. Years ago, Bruce Carnes did a statistics model where he looked at life shortening from mice, dogs, and humans and put them in a single model and showed that there were a lot of relationships, but you had to correct for the age of the animal. They were looking only at life shortening, not looking at and dose, and not looking at dose rate in that. But I believe that using their sort of approach, it's possible to compare different animal models, but to just go from, say, mice to humans is almost impossible. I think you need multiple different species in order to do that. And that's what he claimed as well. It was being able to go from mouse, dog to human that was extremely helpful for that work. So that's important work. It needs to be done. I don't think we yet have a good approach for how to do it.
Thank you, Gayle. And so this is just one of the questions. Again, it's specific to the executive orders for the NRC. How do you think about to reconsider reliance on the LNT model for radiation exposure?
Well, this was already my answer on LNT. And we will not comment on any reorganization in a country like the reorganization now put forward in the US on NRC, for example. This is not, I think, business of ICRP.
Perfect. Yeah, and similar. There's quite a few questions that are kind of similar in nature, so we'll just kind of skip over those moving forward. Was it possible to compare and Gayle, you put your hand up for this one, was it possible to compare the experimental conditions of the animal studies? I guess the experimental design condition also have changed over the past compared to now. Could this might influence the conclusion?
Yeah, this is so cool. We published a paper a number of years ago where we took the data from Aomori in Japan done about a decade ago and compared it to the end results of experiments that were done in the 1980s at Argonne. And in fact, the animals, and it was a similar strain of animal, and we compared similar doses, and in fact, the results were very, very similar except for two things. One was, and this was cancer, ended up showing mostly the same results. Life shortening showed the same results, but the difference was that the GI tract differences and lung infections were different, and we suspect that that's due to differences in food and in circulation within the facilities. But I was shocked at how similar they were. We've actually published that a few years ago with the Japanese, and it was really a remarkable similarity.
Perfect. Thank you, Gayle. So we still have about 45 questions that are open. If anybody on the panel wants to go through that list, and if there's anything that you would in specific like to answer before we close, please feel free to take a look. Otherwise, I'm just basically going top down. So,
Kelsey, may I ask you how we will proceed now with all the questions? There are many more, and we couldn't answer every single question. I mean, we can download those questions, and we could try to find answers, but often the questions came from anonymous listeners, so we cannot directly answer those questions. So how should we proceed?
Yeah, so what we've done in the past is the question might be from an anonymous attendee, and basically what we could do is just basically we can answer the questions regardless of the attendee, and we can post the responses on the event page afterwards. So people, exactly, when they're reviewing the recording afterwards, there'll be a link to essentially view all of the responded questions, and whether or not we might not even write who asked the questions. We'll just have the question and then the responses afterwards. So again, considering how many questions are still open and out there, this might take some time for our panelists. Again, they are all here on a volunteer basis and do have other responsibilities with their jobs. So I can't guarantee that all of these responses are going to be up in a week or so, but we will definitely do our best to have them up in somewhat of a timely fashion for people to review. So we've got time here for a couple more.
I can take Mike Boyd's question about the infinity.
Yeah, perfect.
So Mike, look, what we were trying to show with that is we actually did the model that Beer 7 used for their calculations, and we applied, but we took it now with 120,000 animals instead of with the very few animals that they had used, and we used exactly the same method. And we got sort of impossible numbers with it. We got the lower range was reasonable, but the upper range was not. And that's when we realized that we can't use the entire range for the calculation, and we need to go to smaller ranges, like using limits up to 4 gray or to 3 gray, which is what we did much later. But it was because we allowed for the entire range of doses to be used in those calculations. And I'm happy to talk with you about that further if you want to.
Perfect. Thank you, Gayle. I'm just going to kind of spot a few here randomly kind of down the list. Can you please comment on the reason for not analyzing blood cancers in this review?
Well, the reason is that ICRP doesn't apply the so-called DDREF for leukemia. And the reason for this is because for leukemia, we know that a linear quadratic dose model fits the A-bomb survivors quite well, the data from the A-bomb survivors quite well. And so in this case, with the curvature already explicitly taken into account, ICRP felt that in that case, there is no need to include the DDREF. But in principle, we could also have looked at dose rate effects among leukemia. This was discussed in the early phase of our task group, but the decision was just to focus first on solid cancers. And the reason is also that for leukemia, we have not DDREF applied in the system so far, currently.
Thank you, Werner. And I'd say we have time for two more questions. Maybe this is if there's, again, for the panelists, if there's something in the list of outstanding questions that you would like to answer, please feel free to do that. Otherwise, sorry, I just I lost my place.
But Casey, I think we can come to a conclusion now because it's almost 4 o'clock. So we had 2 hours now.
For sure. Definitely. So I'll just ask this one last question because I think it might be a good one to end on, even though you have touched on these points at some or different points throughout the last few hours. But the draft report stated, it is concluded that current assumptions made in radiological protection, including linear no threshold model, are not in contradiction to what is presently known on the process of cancer development and on cancer risks at low doses and low dose rates in human populations. What should the reader take away from this statement?
Well, just what we tried to say. So to me, it's not clear what's unclear with this statement. Maybe if you would like to send me an email directly that we can continue the discussion on this, because it's an important question. Sure. I mean, if you have no clue what to take with you from the main points we tried to formulate, then maybe we did something we could do better, at least if you help us. So if there is any, and this holds, by the way, for all of you, for the whole audience. We try to work with your questions, of course, but if you feel that you could more directly, if you should address us more directly, then please do so. And send us questions, comments, critics, everything is welcome. And you can also do that. I mean, the report is still open for public consultation, as I said, until June 13. So you can comment as an individual. You can comment on behalf of your organization, of any organization, if you have the mandate. And any of those comments will be read by the task group, that's for sure. This is the promise. I do not promise that we include all changes you propose, but at least we take all the comments seriously, which come on our which will come on our website. So please use also this channel, but also send us emails if you like.
Perfect. So yeah, so that is a great probably place to end for today. Werner, did you want to add anything before we close?
No, that was already my closing statement.
Perfect. So yeah. So thank you everybody for coming today. Those inquiring about a certificate of attendance, that'll be provided to you probably by the end of the week, and it'll be automatically sent to anybody who attended over half of the session today. Otherwise, thank you for joining us. We have another online event next week. It's the Medan Rahani Award Lecture by Francois Paquet from France, and it's the first one of those, so certainly take a look at icrp.org to check that. Thank you to everyone who paid for one of the tickets to join today. It's much appreciated. It allows us to keep doing what we do. And with that, thank you kindly, and we will see everybody next time. Thank you so much.
Thank you.